the nature of energy, some key definitions. Okay, so thermochemistry. Thermo refers to heat or energy. So thermochemistry is the study of the relationships between chemistry and energy. We need to understand scientifically what energy is. Energy is the capacity to do work, which leads to the question, what is work? Work in science is a force acting over a distance. And then heat. Heat is the movement of energy that's caused by a difference in temperature. So energy can be exchanged between objects through contact. So if you hold a hot cup of coffee, you feel energy being transferred from the hot coffee in the form of heat to your cold hand, and it warms up your hand. Any questions about these yet? So a lot of these words we use in everyday language, but they mean something a little bit different. Like you say you're going to work, right? That means you go to your place of employment. Here, work is a force acting through a distance. So we can think of energy as being a quantity that something can possess. A lot like money, right? Money is something that a person can have, and you can transfer it to other people. So here we're looking at a rolling billiard ball. So this billiard ball rolling across the table has energy due to its motion, has kinetic energy. Heat and work are different ways that energy can be exchanged between two objects. So when this ball that's moving collides with this stationary ball, what happens? The purple ball that was sitting still starts to move, right? Because it got hit by the white ball. The white ball did work on the purple ball. It transferred some of its energy to the purple ball through work. And then that second ball, the purple ball, is going to roll away. So energy can move into an object or out of it, just like money can move into your wallet or your Venmo account and out of it, right? I have to stop talking about checking accounts because most people don't have checks anymore. Obsolete. So there are different types of energy. The two big categories are kinetic energy and potential energy. And then the others kind of fall into one or the other. So kinetic energy is the energy of motion. Thermal energy is a subset of kinetic energy. It's a form of kinetic energy. It's the energy associated with temperature. So we've learned that temperature is a measure of the average kinetic energy of, say, a collection of gas molecules. And if you increase the temperature of the gas, what happens to the speed at which those gas particles are moving? It goes faster, right? That movement is the kinetic energy. So thermal energy is associated with temperature, but it is also kinetic energy because now we're looking at the movement of the particles in the substance as opposed to, say, a brick flying through the air having kinetic energy. The other broad category is potential energy. So this is energy that's stored in an object. This energy is going to be associated with either the composition and or the position of an object. So a ball raised above the table has potential energy due to its position relative to the Earth's gravitational field. So here I have a couple of keys. And if I hold them out here at shoulder height, these have potential energy. Because if I let go of them, what's going to happen? They're going to start moving, right? They're going to fall. We do that every single time. So that potential energy they had by being held above the surface of the floor, when I let go of them, that potential energy became transformed into kinetic energy. As they got closer to the floor, their potential energy got lower and lower, but their velocity and thus their kinetic energy got greater. Yes?
So potential energy, is it reliant on something else? Like,
Well,
if
it's
the key moves because you let go.
it's dependent on the position. So they have potential energy here, even if I don't let them go.
Okay.
Because there's the potential, right? So potential energy is not the demonstration of the energy, but it's the potential to demonstrate the energy.
Okay.
So there's
So the
position.
energy's there if it's possible.
Yeah, the energy is there. It's just, are we going to release it or not?
Okay.
So compressing a spring,
Yeah.
pushing down on it, you've given it potential energy. Because if you let go, it's going to go boing and spring back up, right? Chemical energy is a kind of potential energy. This is the composition part of potential energy. So this is associated with, again, position, but relative positions of the charged particles that compose matter, electrons and protons. So some compounds are like compressed springs. They have a lot of potential energy, which can be released in a chemical reaction.
I'm kind of like backtracking a little bit, but
That's okay.
potential energy same thing? Like, can it be the same thing as kinetic though?
Well, no. You can have potential energy. Well, everything actually has kinetic energy
Yeah.
because all particles are moving,
Yeah.
right? But if I put my keys on the bench, they have the same amount of kinetic energy as if I lift them up above the bench. But above the bench, they have more potential energy, okay? So there's that thermal energy due to the motion of the particles within the substance. And then there's a form of potential energy where, the keys are flying through the air, right? Remind me that they're over there later when I look for them. Okay, so there's different levels of motion, right? Everything is moving. The only time you would have the cessation of movement would be at 0 Kelvin. Absolute zero is where particle motion would stop, which, haven't quite gotten there yet. Really close, but can't get there yet. So then chemical energy, instead of being held above a surface or something, is because of the interactions between the positive and negative charges. If we put something into motion, like letting go of the keys or giving a spark to some gasoline in the presence of oxygen, right? Then what happens? Well, it burns and it releases a lot of energy. Where did the energy come from? It was stored in that compound. Okay, sort of like a compressed spring. Any other questions? So this is a flow chart kind of summarizing all of this. Energy is the capacity to do work. We can have kinetic energy due to motion. And a subset of that is thermal energy, which is associated with the temperature of an object, which is the movement of its individual particles. Or we can have potential energy. This is due to position or composition. We don't do a lot of, calculating the potential energy of something 50 feet above the ground or anything. In chemistry, that's more of a physics kind of thing. But what we are interested in chemistry is the chemical energy. So it's the positions of electrons and nuclei. We have talked about the law of conservation of mass. Mass cannot be created or destroyed in a chemical reaction. Well, there's a similar law called the law of conservation of energy. Energy cannot be created or destroyed. You can transfer energy from one object to another. it can assume different forms, but you can't create energy. You also can't destroy energy. The energy content of the universe is constant. Yes?
So this one doesn't have a caveat like the law of conservation of mass, where it cannot be destroyed in a chemical process.
Yeah, so this one does this one have a caveat? Well, yeah, it does. So in a nuclear chemical reaction, mass can be transferred into energy, or energy can be converted into mass. And that's that E equals mc squared, that equation of Einstein's, right? Energy is equal to the mass times the speed of light squared. So does that happen? Yes, it does happen. Does it happen in a regular chemical equation or a chemical reaction? No, it doesn't. So technically what we have to do is we have to say energy and mass together are combined. Are conserved, right? So that's a great question. So here's the analogy like my keys. You hold the ball above the table. This has potential energy due to the force of gravity that's going to act on this ball. You let go of it, and it falls. Now it's moving, right? It has movement that it didn't have before. That's kinetic energy. As it gets closer and closer to the surface of the table, its potential energy decreases. And so we see that energy can be transformed between potential and kinetic forms. Here's an illustration of a woman putting a ball on top of a spring and pressing down on it. So this is different than gravitational potential energy. This is mechanical potential energy. She exerts a force to push down on that spring, and that stores energy in the spring in the form of potential energy. You release it, and the spring uncoils and propels the ball up into the air. The ball is moving now. The ball has kinetic energy. Any questions? So when we look at energy, when we study energy, we can't really study absolute quantities of energy. What we look at is the exchange of energy between two different things, and so then we have to define what we're looking at. So typically we'll look at the system and the surroundings. So the system is whatever we're interested in looking at. Could be the chemical hand warmer or some other chemical reaction that we're studying. The surroundings is everything else, anything else that the system can exchange energy with. And really, this is going to end up being the rest of the universe, right? Normally, we can think of the surroundings as being a little smaller than the universe, but technically it would be the universe. So with the hand warmer example, the surroundings would include your hand, your glove, the air that's in the glove, even the air outside of the glove, right? Because that's where the heat can be exchanged. So when we talk about conservation of energy, we mean that the amount of energy that's gained or lost by the system has to be equal, outside of nuclear changes, to the energy lost or gained by the surroundings. So the total amount of energy is constant. What's changed is where is the energy. So this is where the analogy of energy being like money is useful. If I have a $10 bill in my wallet and I give it to Alina, right? Is there still $10? There's the $10 is still there, right? It's just that Alina has it and I don't. It's just transferred. We haven't created money. We haven't destroyed money, right? We've just moved it around. And so that's what happens with energy. So if we could look at an energy gauge, like a gas tank on the car, and look at the system energy gauge. So that's the part of the universe that we're looking at, and we see that this is half full. And the surroundings energy gauge is a quarter full. After this transfer, we might find that the system now is a quarter full and the surroundings is half full, because the amount of energy lost by the system is equal to the amount of energy gained by the surroundings. Any questions? Of course, if we're going to measure energy, we need some units, right? So if we have an object with a mass that's m and it's moving at a velocity of v, the kinetic energy is given by this equation. Kinetic energy is equal to 1/2 the mass times the velocity squared. We'll run into that equation occasionally, but we're not going to use it extensively. We're just trying to look at the units here. So kilograms, meters, and seconds are base units in the SI system. So if we have mass times velocity squared, mass in kilograms, velocity would be meters per second, and so velocity squared then is meters squared per second square. This is a unit of energy. And so 1 kilogram meter squared per second squared, that's kind of messy. So we gave it a new name, and we called that a joule. Joule. Abbreviation is capital J. So 1 joule is 1 kilogram meter squared per second squared. This is a relatively small amount of energy. So if you think about a 10-watt light bulb, in 1 hour, it's going to use 36,000 joules. That sounds like a lot. Oh my goodness, it's using so much energy. The joule is a really, really small amount of energy. So we can talk about joules. We can also talk about kilojoules. Remember, we can apply those metric prefixes to any unit. And you could talk about kilo inches, I suppose, if you wanted to. But a kilojoule is just 1,000 joules. Another unit that's commonly used is the calorie. Now, this is something that we think of in reference to food, right? How many calories does this have? So the calorie, this calorie has a lowercase c, abbreviated CAL. The original definition was that a calorie was the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So let's say you had a gram of water at 36 degrees Celsius. 1 calorie of energy would increase the temperature of that 1 gram by 1 degree to 37 degrees Celsius. So there's a relationship between calories and joules. This was the original definition. That definition was changed slightly. So a calorie is now defined as exactly 4.184 joules. Calories that we talk about in everyday life are actually called nutritional calories. And those calories have a capital C. Like, that's not confusing at all. So on an exam, in homework problems, if you see calorie with a capital C versus a lowercase c, that's not a typo. There really are two different things, okay? This nutritional calorie with the uppercase C is equal to 1,000 of the lowercase c calories. So a nutritional calorie, capital C, is equal to 1,000 small c calories, which makes it the same as 1 kilocalorie. Okay. There's another unit that's larger called the kilowatt hour, or kWh. That's what PG&E uses to measure the electricity that you use on your bill. We're not going to deal much with kilowatt hours. There could be a question on homework or something where it's asking you to do some converting. So here are energy conversion factors. A calorie is 4.184 joules. This nutritional calorie or kilocalorie is 1,000 calories. which would be 4,184 joules. And here's the relationship between a kilowatt hour and joules. And then there's this asterisk down here. All the conversion factors in that table are exact. So sig figs are not going to come into play with that. And just to get an idea of how much energy these different things are, we could look at, let's say, the amount used by a human body in running 1 mile, approximately. I don't know about you, but running a whole mile, that's a lot of energy, right? So that would be 4.2 times 10 to the 5th joules, 1 times 10 to the 5th calories, or 100 nutritional calories. And then when you think about how many calories, nutritional calories, are in a candy bar, you're like, oh my goodness, I'd have to run a couple of miles, several miles maybe, to burn off the calories in that one candy bar. Maybe I'll pass. The kilowatt hour running a mile would only be 0.12 kilowatt hours. You do not need to memorize any of those. That's just kind of give you an idea.